In this video, we're going to discuss scheduling, specifically CPU scheduling. We're going to talk about what it is, why we do it, and when we might do it. Some things to keep in mind are the concept of processes and threads, and what we mean when we refer to them when we're talking about operating systems. The process control block, and what that is and why it's important for managing multiple processes. And the concept of context switching and mode switching and the difference between them. Particularly, we're going to be considering context switching a lot in this situation. And finally, the idea of process states. So we've talked about a 2, a 5, and a 7 state model. So just for a little bit more detail, let's go back to the 7 state model very briefly. When we're talking about that, the key thing that I want you to remember is the idea that while a process is running, we may have some event that happens. For example, the process issues an I/O request, which is blocking, and the process can't continue until that I/O request finishes. And in this case, we talk about having the state sitting in the process sitting in one of two process states, that are blocked, versus being in a ready state. And it'll be important to consider like the idea of I/O blocking and ready versus blocked processes. So, what is scheduling? If we step back from the concept of computers and just back to general life, scheduling is just when we have multiple things to do, but we have a limited capability to do things at any particular point in time, and we decide which one we're going to do. So you as a student, when you're working on 4 assignments, you can't actually work on 4 assignments at once. So you have to decide which one you're going to work on next, when you're going to stop, and when you're going to start and switch to another assignment. And the same principle is true for operating systems. So some examples of cases where scheduling might be important are a multi-programming environment where we might have multiple processes that are sitting in that ready state that we talked about before, and all of those are capable of being run. So we have to decide which one we're going to run, and if we make those decisions well, then we can have a more efficient system, and if we make them poorly, then we can have a terrible system. We might have a batch system where multiple jobs are being submitted to get done, and we have to decide which job to run and when. We might have a multiple user system, and we have to decide if we've got multiple users all trying to use the same limited system, we have to decide which user gets access next. A scheduler is the thing, typically the program, which decides what to run next. And when we talk about the decisions for what to run next, we call that scheduling. So before we go into detail about how to do scheduling, when to do scheduling, it's important to understand why to do it. What's the point? And in some scenarios, there might not be any point. For example, if we've got even if we are in a multi-programming environment, if we only have one process in the ready state, then that's the only process to run. There's no careful scheduling decision that needs to be made, just run that process. In older systems, especially systems very early in the history of computing, you had a simple scheduling algorithm. You didn't even have the capability of context switching, so there was no way for you to possibly swap out a process and run another one. You simply, the next program on the tape or the next set of instructions on the punch card were the ones to run. In simple machines, which may only run one single application, such as a specific word processing machine, that thing doesn't have multiple processes to worry about. Or say an embedded system, such as sitting at the system running in a remote control, or your washing machine, or inside your TV, in many cases may not need to worry about handling multiple processes and may not need to make scheduling decisions. So sometimes scheduling is not important, and sometimes it is. Now, the times that it is typically when we have more complexity. So if we have a multitasking or a multi-user system, for example. So an example of why it might be valuable in that process is, let's imagine you're just using your laptop at home. You've got an email client running, and the daemon, which is deciding to process an email. For those of you who don't know what a daemon is, it's simply some sort of background process that you usually don't have control over. But you've got an email daemon sitting in the background deciding to process an email, and it takes 2 seconds. But you want to open another application, so you click on that application. In one scenario, the scheduling algorithm decides to run the email daemon and then run the application. And what that results in is a system which takes 2 seconds to open an application after you've clicked it, which makes the system seem sluggish as far as the user is concerned. In the second scenario, the scheduler runs the application first and then runs the daemon. The application appears responsive because it straight away opens, and the delay in the email daemon is not something that the user cares about, so it's not noticed. So we see a very significant difference in the quality of the resulting system as far as the user is concerned, based on how the scheduling decisions were made. So what we can say there is that the scheduling decisions have had a huge impact on the perceived performance of the system. Now later, some more advanced concepts in this topic, in this course, are on real-time systems, where we're talking about systems that actually have deadlines. And in some cases, correct scheduling decisions can make the difference between the system being correct and the system being incorrect, which can be significant. So we talked about the email daemon concept and gave a simple example, but let's flesh out the idea of times when scheduling may play a big impact on the perceived performance of the system, but we'll talk about it in slightly more generalities. And so I'm going to introduce 2 terms now. I'm going to talk about IO-bound processes and CPU-bound processes. A CPU-bound process is one which spends most of its time doing computation on the CPU. So in these diagrams here, we have these little grey boxes here are referencing time when that particular process is utilizing the CPU, and we'll talk about these gaps here as being time when the process is blocked waiting for some I/O to happen. So in the first case, we've got a CPU-bound process. It spends most of its time in long bursts on the CPU time and relatively little time waiting for I/O. In the second scenario, we have what we call an IO-bound process. In this case, it spends fairly small CPU bursts and spends most of its time waiting for I/O requests to complete. Now, for the CPU-bound process, when that process finishes is pretty much determined by how much time you let it use the CPU. Very little is based on how long I/O takes to complete. But for the IO-bound process, it's the inverse. When that process finishes is pretty much determined by how long I/O requests take. You could swap in a faster I/O device and that process would finish earlier. And you could give it more or less CPU time, and that would have a relatively small impact on when it completes. So some examples. An example of a CPU-bound process might be if you fire up MATLAB and run a long chain of linear algebra operations on very small matrices, so there's very little memory operations, and most of what's happened is computation on data that's already in the cache. Whereas an example of a IO-bound process might be finding a simple checksum, like the MD5 of a large file, where most of the time is actually spent waiting for the file to be read in from disk and very little time actually spent doing computation. Alright, so now that we have those definitions, we can talk about IO-bound and CPU-bound a little bit. Having a mix of IO-bound and CPU-bound processes running allows us to keep the CPU and the IO systems busy, which means that we get a better throughput of processes through the system. Also, a individual process is not necessarily, it's not as simple as the examples I gave you. A process may be somewhere between the extremes of IO-bound and CPU-bound, or may go between those two extremes in its own processing. So a system may spend some time reading a lot of data in from disk at the start, and then eventually consolidating that down to some small amount of data which can sit in the cache, and then spend most of its time processing that. So it would go from being IO-bound at the start to being primarily CPU-bound towards the end. When it comes to scheduling, if we pick an IO-bound process over a CPU-bound process, it tends to delay it fairly little, because as soon as the IO-bound process has executed its short burst of CPU, it will block and we can schedule the CPU-bound process. However, choosing it to do the other way around can delay the IO request a lot. And I'm going to give an example on the next slide that should clarify that a little bit. But the takeaway is that generally we should favour scheduling IO-bound processes over CPU-bound processes in an ideal scenario. So, let's look at why we might want to choose an IO-bound process over a CPU-bound process. If we look at the example that I've got down the bottom, we've got the same processes, so I'm just going to call it process 1 and 2 in each case, where process 1 is IO bound and process 2 is CPU bound. Now in the first case, we've chosen to schedule the execution phase of process 1, which was sitting ready, needed to do a little bit of compute at the start, before process 2. So it does its compute short CPU burst, and then it blocks waiting for IO. At this point, process 2 is able to now start and executes for a period of time, and then after that, process 1 will eventually receive its IO request completion, and then will be able to execute its small extra burst of CPU. So the overall end point for running this chunk of these two processes is this time here. In scenario B, however, we've chosen to execute the CPU-bound process first. What happens is that this is not actually IO delay, this is simply the process being held back until process 2 completes. We have a long period of CPU time utilization by process 2 before this short burst from process 1, and now in this last region I'm pointing to here, we have process 1 waiting for IO. So the overall completion time for this same chunk of compute and IO is over here. And the essential reason is that we didn't have an overlap of our IO time with computation time. Overlapping the two of those allows us to keep the devices, the CPU and the disk, busy at the same time, and allows us to finish both processes shorter. So in this case, we've got an example where scheduling a particular process has created a significant delay in when those two processes finish. And it's a reason why, in general, we might prefer IO-bound over CPU-bound processes for the next schedule. Okay, so we've talked about what scheduling is, and now hopefully I've convinced you that maybe it's an important thing to consider, but when do we do scheduling? And this is why it might be important to go back to the 7-state model diagram and have a good idea of what that is in your head. But times when we might do some scheduling times when we might consider scheduling is when we get a new process arriving. So a new process arrives in and we have to decide, are we going to execute it? Are we going to interrupt other processes? What's going to happen? We'll need to consider scheduling when a process exits. So if we've finished a process, then we now need to decide what is the next process we're going to run. Or when a process blocks on IO. So if a process is waiting for an IO request to finish, it will go into the blocked state, and then we can allow another process to run, like in the example on the previous slide. A similar thing might happen when a process blocks on a lock. Now, you don't need to know what that means yet, but that's still something that we should mention, but we will talk later in the course what we mean by blocking on locks. There might be an IO interrupt occurring. So an IO request is sent, a process waits for it, and that doesn't necessarily mean that the process has to poll. The process may be able to use operating system resources to allow for IO interrupts. So when the IO device has completed the operation and the control can be handed back to the process, it'll trigger an interrupt in the operating system, which will allow the operating system to decide, okay, well now we can maybe rerun the process before. We might even have something happening where we've got a timer running. So where we want to allow a process to run for a period of time, but then we want to stop that and allow other processes to run to try and keep maybe a more responsive system as far as a user is concerned. We don't want the system sitting for 15 seconds running a background process while no other user applications get any CPU time. But basically, we generally will need a scheduling decision to be made when a process can't continue, or when some activity allows us to have more than one ready process and we have to decide which one we're going to run. Now, one point of note is that we did briefly introduce this idea of preemptive and non-preemptive scheduling. I'm not really going to talk about that in this video, and I'm going to very briefly allude to it in the next video, but keep those terms in your head because we are going to be talking about those in the lecture. So in this video, we've talked about what scheduling is, and we've focused primarily on CPU scheduling. There are other forms of scheduling which we will talk about in the course. I've given you some basic ideas of why you might consider scheduling as something important to spend your time worrying about. And we've also given a very brief introduction to times when scheduling may occur.